Electric vehicle batteries are the heart of an EV, the central power source that makes the whole car run. In fact, the battery pack alone can make up as much as 30 to 40% of an electric car's total value, which shows just how crucial it is. But what exactly is inside these big battery packs, and how are they made? Today, we're pulling back the curtain on how EV batteries are built, from raw minerals in the ground all the way to installation in the car. And don't worry, we'll keep it simple and fun. Think of the battery as a giant energy sandwich or a Lego set that powers your car. By the end, you'll see how all the pieces come together to create the powerful battery that lets an electric car zoom down the road. So, where does this process begin? Just like baking a cake starts with gathering ingredients, building a battery starts with sourcing the raw materials. Let's begin our journey at the very beginning, the mines and fields where key battery materials come from. The first step in making an EV battery is getting the basic ingredients. Modern electric car batteries, usually lithium-ion batteries, rely on a handful of critical minerals that are literally dug out of the earth. These include lithium, cobalt, manganese, nickel, and graphite. Think of these as the flour, sugar, and eggs of our battery recipe. Essential ingredients. Lithium often comes from vast salt brine flats or mineral ores. Nickel and cobalt are mined from rocks with major sources in places like Africa and Australia. And graphite, a form of carbon, is either mined or synthesized. Once extracted, these raw materials need to be refined and purified. Imagine you've got rough grains of salt and you need fine table salt for cooking. Similarly, battery materials must be processed into high-purity chemical forms. For example, lithium is typically converted into lithium carbonate or lithium hydroxide powders, and metals like nickel and cobalt are turned into chemical compounds like sulfates that can be used in battery electrodes. This refining often happens in large chemical plants, many of which are in regions like Asia, where a lot of battery material processing takes place. By the end of this stage, we have battery-grade materials, purified lithium compounds, nickel and cobalt salts, manganese, and high-quality graphite, all ready to be turned into the components of a battery. In short, we've gathered the ingredients for our battery. Now it's time to mix those ingredients to make the electrode materials, kind of like preparing the dough or batter in our kitchen analogy. Now that we have our purified minerals, the next step is to prepare the cathode and anode materials, the positive and negative sides of the battery. If the battery is an energy sandwich, the cathode and anode are the two big slices of bread that hold everything together. The cathode, or positive electrode, is typically made from a lithium metal oxide compound. Imagine lithium combined with other metals like cobalt, nickel, manganese, or iron. And the anode, or negative electrode, is usually made of graphite, a form of carbon. In simple terms, the cathode is where lithium ions want to go when the battery is discharged, and the anode is where those lithium ions hang out when the battery is charged. To make these electrode materials, engineers mix the refined powders with a few extra ingredients to create a sort of battery paste. Inside giant mixers, the active material powder, for example, a lithium nickel manganese oxide for the cathode, or graphite for the anode, is combined with a binder which acts like glue to hold particles together, and conductive additives like carbon black, which help electrons flow easily. This mixture is blended with a liquid solvent to form a thick slurry. Picture mixing a very fine, goopy batter or paint. This process must be done very carefully, often in a vacuum and ultra-dry environment because any moisture or air bubbles could hurt battery performance. The result is two kinds of slurries, one for the cathode and one for the anode, each with a peanut butter-like consistency. If you've ever made pancake batter with no lumps, you get the idea. We want a smooth, even paste. Now that our battery batter is ready, we need to spread it out and bake it, so to speak, into electrodes. This is where our battery starts to take shape. The process is a bit like making a layered cake or a jelly roll. We coat cathode and anode slurry onto metal foils, which serve as current collectors. For the cathode, the slurry is spread onto a thin aluminum foil. For the anode, it's spread onto a copper foil. These foils conduct electricity in and out of the electrodes. A machine coats the slurry in a thin, even layer across the moving foil. Any excess is scraped off to ensure uniform thickness. And then, the coated foils go through drying ovens to evaporate the solvent. By the end, we have long rolls of cathode sheets and anode sheets. Once dry, these rolls are compressed by high-pressure rollers, a process called calendaring, to make the electrode layers denser and perfectly flat. This step is important because tighter, flatter electrodes mean more energy can be packed in and a better performing battery. After that, the long sheets are cut, slit into the exact sizes needed for individual battery cells. Now, we have the fundamental pieces, thin sheets of cathode and anode material. The next part is like assembling a sandwich. We stack these sheets together with a special separator in between. Each battery cell is essentially built of these layers, a cathode, a separator, and an anode, arranged like a repeating pattern. Cathode, separator, anode, separator, and so on. The separator is a very thin sheet of porous material, often a special plastic that keeps the positive and negative sides from touching, which would cause a short circuit, but it allows lithium ions to move between the electrodes. We put a separator between every cathode and anode pair. Imagine the separator like the lettuce in a sandwich, keeping the two halves apart, but letting the juice, in this case, lithium ions, flow through. Depending on the design, manufacturers either stack these layers flat, common for pouch and prismatic cells, akin to layering lasagna, or roll them up into a spiral, common for cylindrical cells, like rolling up a Swiss roll cake or a roll of paper towels. Either way, we end up with a neat bundle of layered electrodes. At this point, our battery cell looks like a dry, layered stack. All the key parts are there except one. We haven't added the juice that will carry the electric charge. For that, we need to introduce the electrolyte. Now it's time to put the battery cell together and give it life. The dry electrode stack or jelly roll is placed into a cell casing. This casing might be a cylindrical metal can, a rectangular metal can, or a flexible aluminum-coated pouch. Each casing will eventually be a single-sealed battery cell. With the electrodes snugly in their case, the manufacturer then fills the cell with electrolyte, a special liquid chemical mixture. The electrolyte is like the blood of the battery, carrying charged particles between the anode and cathode. It's usually a lithium salt dissolved in organic solvents. This liquid gets injected into the cell under vacuum conditions so that it thoroughly soaks into all the pores of the electrodes and separator. We want every bit of the electrode material wet with electrolyte, because that's how the lithium ions will travel. In a pouch cell, they'll pour the electrolyte into the pouch. In a cylindrical cell, they often use a syringe-like nozzle to inject the electrolyte into the metal can. Once filled, any excess air or gas is removed to make sure nothing interferes with the chemical reactions. Finally, the cell is sealed tightly. Cylindrical and prismatic cans get crimped and welded shut with a cap, and pouch cells get heat-sealed. Now we have a finished battery cell. Almost. It's assembled, but if you tried to use it at this exact moment, it wouldn't perform at full capacity yet, and it might not be fully safe. First, it needs a kind of wake-up call and quality check, which we call formation and testing. You can think of this step as training or quality assurance for each cell. After assembly, cells undergo a process called formation and aging. What happens here is the cells are charged and discharged multiple times under controlled conditions. The very first charge is critical. Sand helps form a solid electrolyte interface inside the cell. Essentially, we're breaking in the battery. Each cell is slowly charged up to full, then discharged, often more than once. This not only activates the cell's chemistry to its full potential, but also allows the manufacturers to measure how the cell is performing. During these formation cycles, the cell is monitored for capacity and other metrics. Cells are typically stored for a short period at controlled temperature. This is the aging part, where the electrolyte fully soaks in and the cell's internal chemistry stabilizes. If any cell is going to fail early, it will likely show up here during these initial cycles, or the rest period. Some cells might generate a bit of gas during formation, and then they're sealed again. All of this is also a big quality control checkpoint. The factory will test each cell's voltage, capacity, and even internal resistance. Cells that don't meet the standards are pulled out and rejected. The ones that pass get sorted and often graded by their performance. Manufacturers like to put cells with similar capacities together when building battery packs, so the pack performs evenly. By the end of formation and testing, we have a batch of reliable, consistent battery cells ready to be combined into something bigger. One battery cell by itself can power a flashlight or a phone. But an electric car needs hundreds, sometimes thousands, of these cells working together. The next step is to connect cells into larger units called modules and add systems to keep them cool and controlled. To build a full car battery, individual cells are first grouped into modules. A battery module is like a building block containing a set of cells. Think of it as a Lego block made of batteries. For example, a module might contain a few dozen cells connected together. Cells can be connected in series and in parallel depending on the design. They are linked by bus bars or heavy-duty connectors. The cells are usually mounted in a frame or enclosure to keep them secure. Inside a module, there may also be sensors and sometimes fuses or other protective devices, so that if one cell fails, it doesn't take the whole module down. Now, as you might know, batteries don't like getting too hot or too cold. Temperature affects their performance and lifespan. So modules are designed with cooling systems in mind. Typically, as modules are assembled, manufacturers integrate thermal management components. This can take the form of coolant channels or plates that run between or around cells. In many EV battery packs, a liquid coolant is circulated through these flat metal cooling plates that touch the cells or modules. If you look at our module example, imagine a flat plate with serpentines of tubing. Coolant flows through that to draw heat away from the cells. Some designs use cooling tubes snaking between rows of cells. Others use cooling fins or even direct cooling where coolant touches the cell surfaces. There are also thermal interface materials used to help conduct heat out of the cells and into the cooling system. All of this keeps the battery modules from overheating when you're fast charging or flooring the accelerator. It's like giving the battery its own radiator system. Keeping temperatures in check also means the battery can deliver high performance and long life safely. Now, all the pieces come together. Building the battery pack is like assembling a puzzle out of modules. The modules are arranged inside a sturdy pack housing, and they're all connected together electrically to form one big battery. This involves connecting the modules in series or parallel as needed to get the overall pack voltage and capacity required for the car. Those connections are made with robust bus bars and cables. By the time we're done, the pack behaves like one giant battery made up of many cells. If modules are Lego blocks, the pack is the final Lego structure. In many EVs, this pack spans the base of the vehicle, often the entire floor of the car, both to save space and to keep the car's center of gravity low for better stability. But a battery pack is more than just modules and cells. It also has a lot of intelligence and safety built in. The most important part here is the battery management system, or BMS. The BMS is often called the brain of the battery. It's essentially a small computer, or a network of several units for big packs, embedded in the pack. Its job is to constantly monitor and manage the battery's condition. It keeps track of things like each cell's or module's voltage, the temperature at various points in the pack, and the current flowing in or out. If any cell is getting too hot, or if voltages become unbalanced, the BMS will know. It can communicate with the car's other systems, for example, telling the motor or charger to slow down if the battery is too hot, or in an emergency, disconnecting the battery to prevent damage. Think of the BMS as a battery babysitter, making sure every cell behaves and distributing the workload evenly, or even as an orchestra conductor, ensuring all the cells play in harmony. Along with the BMS, the pack includes cooling and safety systems that we touched on earlier. All those coolant channels in the modules get linked to the pack's thermal management system. That means pumps, hoses, valves, and sometimes a radiator, all integrated so that coolant can flow through the battery and then release heat to the outside. Many packs also have heaters for cold weather to keep the battery warm in winter so it can operate efficiently. On the safety side, packs can have built-in fire protection, for example. Special fire retardant materials or liners between cells that can slow or stop a fire. They also have electrical safety devices, contactors, high voltage switches that can disconnect the battery when the car is off or in a crash, and fuses that blow if there's a short circuit. The whole pack is enclosed in a robust housing, usually metal, to protect against impacts and to be watertight, since you don't want water getting into a high-voltage battery. When all modules are in place, the BMS and other components are installed and wired up, and the cooling lines are connected, we seal up the pack. Now we have a complete battery pack. Before it ships out, however, there's one more crucial stage: quality control and safety testing of the pack. Building a battery pack isn't just about assembling parts. Every step includes quality checks. By the time a battery pack is complete, it has already been through numerous tests. At the pack level, it faces even more rigorous scrutiny. Manufacturers perform end-of-line tests to ensure safety and robustness. Tests include electrical, charging, BMS, and environmental simulations. Packs undergo temperature, vibration, and watertight tests. Safety standards are strict, including crush and puncture tests. Only after passing all tests is a pack cleared for installation. Let's head to the vehicle assembly line and watch the installation. Here we are at the grand finale. The car is almost complete. It has the motor, wheels, body, everything except its heart. The battery pack is brought to the assembly line and carefully lifted into the vehicle's frame. In many modern electric car designs, the battery pack is installed under the floor of the car, between the axles. This not only saves space, but also gives the car a low center of gravity, which helps with stability. The pack is bolted securely to the chassis. It's actually a structural part of the car in some designs, adding stiffness to the frame. Heavy-duty electrical connectors are then attached, the main positive and negative cables that connect the pack to the car's power electronics and motor, and various smaller connectors for communication and sensors so the car's computer can talk to the BMS. With a satisfying click and whir of tools, the battery pack is now in place, connected, and the car comes alive electrically. At this point, the EV is effectively fueled. The battery pack holds the energy that will drive the electric motor. The assembly team might do a final check, making sure the high-voltage system is functioning. Then, the car gets its body, panels, interior, and final touches. Soon, it will roll off the assembly line. When you, the driver, eventually buy this car and press the start button, the car's systems will draw power from that very battery pack we just saw being made, and you'll silently zoom away on pure electric power. And there you have it. Our journey went from mining rocks and extracting liquids in far-flung places all the way to a high-tech battery pack bolted into an electric car. We saw how raw materials are transformed into powders, how those powders become layers in a cell, how cells are like energy sandwiches filled with electrochemical jam, and how thousands of these cells are linked like Lego bricks with cooling and computer systems to make a safe, powerful EV battery. It's an amazing blend of chemistry, engineering, and technology. Next time you drive an electric car or see one on the road, you'll know a bit more about the incredible journey that its battery made, a journey empowering the future of clean transportation. Thank you for joining us on this battery building adventure. Safe travels and happy charging.